Hello students, today we are going to study conservative force and its example. What is conservative force? There are certain forces, for example, gravity, which have a special property that we call conservative. We know that when an object is moved from one point to another by applying a force F along a curved path, then total work done in moving an object is W is equal to integration from point A to B vector F dot vector dr. In general, work done depends on the nature of the path, but in special cases it does not. Conservative force is any force necessary to move a particle from one point to another point. If work done in moving an object from one point to another point is independent of the path, the force is called conservative force. The work done by conservative force depends only on positions of these points and not on the path followed. The work done by a conservative force on an object moving through any closed path is zero. Gravitational force, electrostatic force, elastic force, and magnetic force are the examples of conservative force. But gravitational force or gravity is a special example of conservative force. Conservative force results in stored or potential energy. We can define a potential energy for any conservative force. For example, an old-fashioned watch, you do work against its spring and store energy in it. This stored energy is recoverable as a work and is useful as a potential energy contained in a spring. The reason that the spring has characteristic that its force is conservative. As the name suggests, conservative force conserves energy. Then properties of conservative force. If a force has the following properties, then it is said to be a conservative force. First property is, when we consider a closed loop, the total work done completed by conservative force will always be zero. Second property is, total work done in moving a particle between 2 points is independent of the path. Conservative force depends only on initial and final position of an object. The work done by a conservative force is reversible or recoverable. So these are the properties of conservative force. Let us imagine the particle be moved from point A to point B along path 1. This is point A, this is point B. Initially, particle will be placed at position or at a point A. Then it will move from A to B along path 1. So this is path 1. The work done along path 1 is, means from A to B is, suppose W1 is equal to integration from A to B vector F dot vector dr. Similarly, particle will also move along path 2. Then work done along path 2 is, suppose W2, which is equal to integration from A to B vector F dot vector dr. So from above equations, W1 is equal to W2. Means work done along path 1 is same as work done along path 2. If we consider W1 and W2 both have the same starting and ending points, then we get W1 is equal to W2. That is, work done along path 1 is same as work done along path 2. Then the force F is called conservative force. In this case, work done on the particle is independent of the path, followed by the particle between 2 points, but depends on positions of these points. Thus, a force is called conservative if the work done by it on a particle that moves from one point to another point depends only on positions of points and not on the path followed. Then consider another situation. Means consider the closed loop ABA. And closed loop is a system where the body returns again and again to the same position. For example, a mass on a spring, then a bouncing ball, uniform circular motion, etc. So let us consider the closed loop ABA. Since the total work done over the loop must be 0 for a conservative force. This is the property of conservative force, and we consider a closed loop ABA as shown in figure 2. This is point A, this is B. So, if work done in moving the particle from point A to point B, that is along path 1, is W1. So, we get W1 is equal to integration from A to B along path 1 is integration A to B vector F dot vector dr. This is value of W1. And work done from point B to point A, that is along path 2, is W2 dash. Means from point B to point A. Means point A goes to its initial position. So we call as a loop. So we get W2 dash is equal to integration from B to A vector F dot vector dr. So in this, from figure, we get value of W1 and W2 dash. We have to show that total work done is equal to 0. The total work done for round trip journey or a closed path from point A to point B through path 1 and from point B to point A through path 2 is W is equal to W1 plus W2 dash. This is total work done. The work done in moving a particle from point A to point B along path 2 is W2 which is equal to integration a to b f dot dr vector dr. This is value of W2 from figure A or from figure 1 along path 2, and W2 dash is equal to integration B to A vector f dot vector dr. When we observe these two values, then we can write W2 dash is equal to minus W2, because in case of W2 integration is A to B, and integration in case of W2 dash integration is B to A. Only limits are interchange. So W2 dash is equal to minus W2. Hence total work done W is equal to W1 minus W2. Putting value of W1 and W2 here. For conservative force field, W1 is equal to W2. Hence we get W is equal to integration from A to B vector f dot vector dr along path 1 minus integration from point A to B vector f dot vector dr along path 2. So both are same, but sign is opposite. So they get cancelled and we get W is equal to 0. Thus the total work done during round trip journey or a closed path is equal to 0, and the force is called conservative force. Then prove that gravitational force between two material bodies is a conservative force. Or total work done in moving an object of mass m under the effect of gravitational force along a closed path is 0. So for that, consider a body of mass capital M placed at the origin O as shown in figure. So let us draw the diagram. Another body of mass small m be moved from point A to point B along path 1. Due to the effect of gravitational force exerted by body of mass capital M on the body of mass small m, so let us first calculate the work done by gravitational force F in moving a body of mass small m through small displacement ds. So this is x-axis, y-axis, this is origin. A body of mass capital M be placed at the origin. Another body of mass small m be moved from or be placed at point P and is moved from point A to B along path 1. Let r is the distance of point P from origin O. This is point A, point B, and the body of mass small m be moved from point A to point B. Let ds be the small element on AB, curve AB or along a path 1. Let RA be the distance of point A from origin O. Similarly, RB is the distance of point B from origin O. And this is again particle or a body of mass small m goes to point A along path 2. So this figure shows gravitational force between two bodies. One body which is placed at origin having mass capital M, and another body will move along path 1 of mass small m, be placed at a point P. So for the small displacement ds, work done will be small, that is dw, which is equal to vector f dot vector ds. This is basic definition of work done, and dot product of two vectors is f ds cos theta. From figure we get ds cos theta is equal to dr. For that, as we consider ds is the small element, similarly dr with the small element along this vector r. So we get dr here. So dw is equal to f dr. The gravitational force exerted by the body of mass capital M on the body of mass small m is F is equal to gmm by r square. Putting value of F, we get dw is equal to gmm by r square dr, where r is distance between point P and origin O. G is gravitational constant, which m is constant, then small m is also constant. So we get the work done in moving a body from point A to point B along path 1 is W is equal to integration dW, means integration from A to B gmm by r square dr. That is W is equal to gmm integration A to B r raised to minus 2 dr, and integration is work done from A to B gmm minus 1 by r from point A to B, means work done from A to B is equal to gmm into bracket minus 1 by RB and minus plus 1 by RA. So let us first write positive term. So we get 1 upon RA minus 1 upon RB. This is the work done in moving a body of mass small m from point A to point B along path 1. From above equation, work done by gravitational force depends only on the position of 2 points and not on path. Similarly, work done in moving a body of mass small m from point B to point A along path 2 is work done from B to A is equal to gmm into 1 by RB minus 1 by RA, means work done from B to A is equal to integration from point B to A gmm by r square dr, and by solving this we get finally work done from B to A gmm into bracket 1 by RB minus 1 by RA. Hence, adding these two equations, we get work done from A to B plus work done from B to A, means total work done, is equal to gmm upon into bracket 1 upon RA minus 1 upon RB plus gmm into bracket 1 upon RB minus 1 upon RA. So gmm is common, which is equal to gmm into bracket 1 upon RA minus 1 by RB plus 1 by RB minus 1 by RA. So first term and last term are same but opposite in sign, so they get cancelled. Similarly, second and third term also cancel. and which is equal to 0. So work done from A to B plus work done from B to A is equal to 0. Means total work done is 0. Thus work done in moving the object of mass small m under the effect of gravitational force along a closed path is 0. So gravitational force is a conservative force. Thank you.